go back. Oh, so let me. Okay, so we wanted to see that we're assuming ADR plus theta regular. CH, we can force CH plus there is an omega 1 dense ideal on. Am I sharing this?
No, I don't share screen now.
Right, okay. Just a second. There is an omega 1. So let me share this. Maybe that's what the problem is when I share stuff. Can you see me now? Can you see the
Yes,
board
we can
now?
see, we can hear.
Okay, sorry. This is a new, maybe I should say this in the recording. This is a internet that they installed, which made, it's supposed to be super fast internet that we have. Okay, so we want to continue the proof, and the key lemma was we have to prove something about non-stationary ideal. The non-stationary ideal is precipitous. So for that, you need to analyze you need to have some control of the clubs. What characterization of clubs, and this is the one. We want to prove that if a condition forces S contains a club, then S contains them in V, right? The club of countable things with this property. Now the issue is that it's a bit unclear what it means to say for omega many generics G, which are subsets of our forcing, right? This was supposed to be the explanation. Since P sigma is countably closed, since P is countably closed, here I wanted to say since P is countably closed, if G is P sigma is sort of LP intersection sigma generic, then union G is a condition, is in P. So by G forces blah blah blah, we mean union G forces blah blah blah, right? So that's one thing. Another thing is that we can have since LP intersection sigma thinks that this P sigma is countably closed. Well, I don't actually need that. Well, closed. If H is LP, H is generic over that model, is generic, then do I really need? So I need a little bit more, right? So if H is generic over what? Or if H over P sigma is generic over, I guess this line is irrelevant. This is irrelevant. If you pick a generic, is generic over L, you need a little bit more than that, right? You need powers of variables. right? So you need enumeration of power set of reals of L P sigma sigma. Then we can find a generic for P sigma in L P sigma sigma H. So in other words, it makes complete sense to talk about this notion of Comigre relative to sigma, right? So I can really say, even though, in other words, I mean, not, the notion is the same. The P seems to have a different topology than the Bayer topology, but it doesn't matter. We can still, because of this, we can still talk about what it means to be Comigre. So you could think of it as saying for Comigre many such H, if you look at the corresponding generic, then that generic does something. You can think of it that way, for example. Right? So one can make sense of or call Niger many G subset of K sigma, right? Because P sigma again, it's not the Bayer space. Okay, so long story short, we already proved A to B, so let's go from B to A, and this is the most interesting, in my opinion, this is really the most interesting part of this proof, of the whole proof. So what do we do? So now we let A, right? So I have this condition, so you have to remember what the condition is. This condition. And I mean, let's just try to understand what the condition is. For a club of countable things, countable sigma in P omega 1 of R. So for this, you have to think of club of countable substructures of V, right? Because the club of sigma are set of reals of some countable substructure. Okay, so for club of things like that, if I enumerate sufficiently enough initial segment of that countable substructure, I can find a generic for my P sigma, which forces sigma is in S. Okay, all right, so that's the property we have. Now, let A be the set of Qx. So Q is going to be a condition in P. X is going to enumerate and enumerates some sigma in P omega 1 of R. So it's some countable thing. And we want to say that Comigre and we're going to say that Q forces so the sigma that X enumerates, right, is in S. So what is this set? What is this set anticipating? Think of what the set is. So remember, every set of reals is universally Bayer, at least are universally Bayer. So every equation you write, that's an anticipation of something. Okay, what is it an anticipation of? This Q will be a generic enumeration of all reals, right? Is Q. And X will be the particular, I mean, Q will be the generic of that we get X. The typical X is the enumeration of reals in order type omega, the set of all reals. And Q will be the generic you get out of it. Okay? You can hear me, right? Yeah, okay. So think of Q is our P generic, X is our all omega R generic. This is how you should think of the situation. That's what the set A anticipates. Okay, now we want to use the kind of universal pairness that we have. Okay, so for that we have to make A a little bit bigger. So let B be a set of reals such that L, B are things, A is RUB. If you remember, what that means is that all I have to do is there are these trees for A, and I have to let B be a set of reals which codes the trees for this to work, right? Okay. All right, so the next thing to do is, okay, so for sigma in P omega 1 of R, I want to look at M B sigma, and this will be L B intersection sigma sigma, right? So I want to look at, consider only those sigma such that what? Such that the reals of M B sigma is exactly sigma, so we don't want to have more reals. Okay, and now we want to say, now if I do a small forcing over this, right? Any forcing that enumerates sigma. So for any, this is really a recall because we talked about this. Recall if H now from omega to sigma is MB sigma generic, then we have this triangle. We have this LBR, right? This is my MB sigma. So we have an embedding here, I, and the embedding is generated by just moving B intersection sigma to B and reals, fixing the reals. And here we get what? Here we get the L. Oh, sorry, I want to look at LA sigma here now because I want to apply this for A. So what I want to do is I want to look at A here, right? So I have LAR and A sigma. And here I want to look at LAH and RH. But from what perspective? From the perspective of MB sigma H, right? And we have this other embedding. So we have I here and J here. And let me make this clear. So this is MB sigma H, right? So H is generic. We go to the generic extension. A is universally bare, so I can interpret A into the generic extension there. Can look at the new reals. And we argued before that there is an embedding into the big parent model. This guy embeds there. And the triangle commutes, of course. Okay, so what we're going to do is look at what we now know about this situation. Right. So what is this H? How are we supposed to think of this H? See, H is this X, right? And there's going to be a Q. Okay, so what is going to be this Q? All right, so we know, right? So applying B, we get what? What do we get? Look, what do we get? We know that G, sorry, let's go back to B. B is saying for club of sigma, the omega many generics, they're gonna do this, right? So I'm gonna if I pick, we get if sigma is as in B, right? Then for omega many G, containing P, omega many G containing, I should have probably omega many G containing P. Sorry, what happens? G forces omega many generic G containing P. G forces the sigma check is in S, but this means that so for omega many G H sorry GH belongs to A, where H was my generic. See, I'm saying where H is enumeration, generic enumeration. Right? Because I already know this property. I know that I have, if I take a sigma with this property, then I know there are omega many G's which contain P, and I'm going to do for sigma is in S. So if you pick any enumeration of that particular sigma, doesn't have to be generic. Any enumeration, it will have this property. But now this is first order over MA sigma. What does this say about imagine? Now this is first order because of the triangle above. This means this triangle, right? This embedding. See, this H, just look at the embedding. The force over this model, that's this little H that comes in, right? Okay, that little H gives you, let's say, another generic. You have, gives you this G, this little G. Yes? And now you know that that pair is in A, is in this big A. The pair is in this big A, but because of J, you know that it's in AH. So what we know, this means that M V sigma thinks that P forces, right? That P forces in what forcing? In P sigma forcing, that it is forced by who? By the club's omega sigma, right? Which is what H is. So it's forced by that, G. So P forces that G be the name. So I'm putting G here to say that that's the name for this generic, and I'm putting H here to say that that's the name for this generic, right? So it's for that G, yeah, G and sigma H, it belongs to AG star H. So this is what we know. Just, I mean, if it, sigma H is, well, sigma H is just sigma. It doesn't have to, I don't have to write sigma H. I should write H, not sigma H. It should be H. Just, if you look at what it's saying, you'll see that it's kind of, okay, so I know that GH is in where? Because sigma has this property that we have, that means there are omega many generics that force little sigma belongs to S, right? So there are omega many generics that force that. That means for omega many generics, if I pair G with any H, which enumerates that particular sigma, that's going to be in A. Okay, but now think of this embedding. Any such G paired with any H, which exists in this in the right side of this embedding, this one, yes, is going to belong to A sub H. Why? Because that embeds into A. That pair exists in A, and J is identity on reals. So J of G comma H is actually G comma H. So we have the end of the day, this is because J of GH is actually GH. This is why. Okay. So this is why we have what we have. And why is it that P forces it? Well, because there were omega many generics. Okay. That's why we need to know that there are omega many generics. If P doesn't force, then there is an extension of P which forces the opposite, and you could find a generic with which is in your omega set and contains that other condition. You will get a contradiction. So the fact that P forces follows from the fact that there are omega. Remark: P forces part follows from the fact that there is a omega set of generics. Okay. So why does this good? Well, all we now need to do. So in working in VGA now. Okay, so now let's go to now pick G, which subset of P, V generic, such that P is in G, right? And now I want to find, so now we can find, we have a club of sigma in VG, such that M B sigma G is an elementary substructure or embeds, right? I shouldn't write this way. I should write there is an embedding such that there exists some embedding K from here into G intersection B sigma into L B sigma G. Right? If you just take a countable substructure of this universe, so K is really a column hole of, for example, L B sharp sigma G, for example. Just take a countable column hole, you'll end up with one of the other structures. And remember, P is countably closed. So this is, you end up exactly, you don't have new reals, right? So what do we now know? That's the P over this model, that's a generic, right? So over this model, P was forcing something. What was P forcing? We go back to here. So this G intersection P sigma is generic over that model. And so what does P force? P force, if you take the generic, then that generic is going to make sure that force, that sigma, belongs to S, right? Remember, A is what? Let's just go back, check what A is. A says this Q, right? This Q is supposed to force that sigma is in S, where sigma is the thing coded by X. And so this is a generic. So G intersection P sigma, and any H I take is in A, where H is just enumerating sigma. But what does this mean? This means that that thing, right? So G intersection P sigma forces that sigma is in S. But this is a condition, right? But G intersection P sigma is a condition. You can think of it as condition, meaning, right, in G. So G thinks sigma is in S, right?
Gregor, I'm sorry, like I was trying to figure it myself, but going back to the triangle, why actually? Because like the triangle suggests that the embedding from MA sigma to LAR is elementary.
Yeah, the triangle would say that J is elementary.
Okay, so you're
This
not claiming.
one,
Okay. So it's elementary because it's complete. Okay.
yeah, that's part of
I was
the
okay. Because that's
of the embeddings are. Should I write here that the embeddings are elementary?
No. But I was confused why pi is elementary. But this okay. But the logic you applied here, it is elementary precisely because you can complete the triangle to I and J.
Oh, why this? Well, this could be, for example, like Scholemhall, right, of A sharp
Yeah, but then
or B sharp.
is it clear that maybe I'm just struggling with the definition of comeagre. I kind of so now you
Wait,
took
Comiga here. So this is not about Comiga, right? This is just about UB. This is from. This is from. Oh, so it's RUB. The stronger version of RUBness that we proved. The first pi, so pi comes from typically, it's the same way you get pi would be like a Scholemhall of, let's say, it was the B, yeah? For example, if you take B sharp and you take a countable substructure of it, right? There will be this embedding pi because it will act on A sharp, and you could then if some sharp embeds into A sharp, then you leave the theories, so you have pi. Okay, but then I is the basically sealing strengthening of this UB fact. So it's not only things are UB, but you also have this elementary embedding. And J is again the sealing part of this UB. So this is just a pure determinacy thing we did a few weeks ago.
Okay.
But the trick here is but it's a bit tricky. The trick is that okay, so we have this embedding, but I know that the generic, this G, and any enumeration of sigma belongs to A, right? And therefore it belongs to AH. So I know that that if I enumerate sigma, sorry, if I force by P sigma get my G and enumerate sigma, then the pair ends up in the extension of A. I mean, this is there's something tricky happening here. I don't know if you guys paying attention to that. Somebody wanted to ask question.
I was wondering the fact that there is such a elementary map pi. This is true for club many sigma, right? Not or sigma.
Yeah, for club of sigma, this is true.
I think that might have been the confusion.
Right, it's not for every sigma.
Obvious, yeah. You cannot just take any sigma, but
right. So you see what I concluded. This conclusion should be confusing. I guess the confusing part here is this, right? This is okay, but why is this true? It's saying if you pick a club, I mean, I know that for Comic many generics G, any enumeration I pick, it will be in A. Then because that's identity, the I mean the J or whatever which embedding was that the J is fixing any particular real. So this will be G and H will be fixed by J. So I know that GH must be in the lift up of A. But the meaning is preserved. A sub G star H has the same meaning as it had in A. So this is still the set of those things, right? I mean, that's the trick here. Maybe I should put a remark here. We have that, and this is because of J, that M B sigma G star H thinks that AG star H is the set of conditions QX. Q is a condition in PG star H. X enumerates some tau in P omega 1 of R, which in this case is the new reals, right? And Q forces that tau is in S. It's the same set S. And just think for a second, right? What this is saying is, I'm told that Saharon, right, in his book, sometimes writes proof, think. This is one of those things. I don't know if I can explain it, but you have to think. It's a bit tricky. So you have that the meaning not only that GH is in A, but this A has the same meaning as it had before. So it's the set of pairs QX such that X enumerates something and Q forces that something belongs to S. Now locally, but this S, it's the same one. Here we should have. I should really be writing. We should be writing S dot G star H, but right, because it's not the full universe. I cannot really talk about S, but this is the same S, the embed because of embedding, but JS dot G star H is S dot. So we have Q forces tau is in S. So we really do have this. Okay, it's the way I wrote it. It's not technically correct. It should have been G star H because in this model I don't know what S is. I only know what this is. And then you can ask, okay, but S is just a name for stationary set. Well, a name for a stationary subset of P omega 1 of R is coded by a set of reals. So this is really a question about that particular set of reals that codes the name for such an S. Yes? Okay, should I go on? Or it was clear or confusing?
I have one more question. Can you show again the forcing statement? P forces.
Which
I've not seen the notation. I was just wondering, is that the notation with the G and the H over the forcing symbol? Is that just
So
saying
what
you're
I
using?
meant, yeah, this is what NUM is using in the paper, and just to mean that G is the name for the generic and H is the name for the generic.
Okay, thanks.
Right. I don't know if it's standard, I don't know, but NUM is using that in the paper. So
Can you quickly show the definition of capital B again?
the definition.
Yeah.
Yeah, capital B, we pick it, so we know that A is RUB. ADR, remember, we proved that ADR implies every set is
Yeah.
RUB.
Okay.
But that is witnessed by some set of reals. So there is set of reals. Basically, the tree T and S, which witness that A is RUB, is coded by a set of reals. So all we do is we take a set of reals which codes the pair of the trees, and that's my B. So this
Okay.
B codes, yeah, and then it's listing, right? This is if you look at the PMAX book, this type of idea comes up so many times. Very, very kind of a cute argument, I think. Right. Okay, so why we need this? Let me wrap it up by telling you why we need this. And then next week we will, well, what does this give you? This gives us that ns omega 1 is precipitous. So corollary, ns omega 1 is in V GH, where G star H is subset of all omega 1 R add one coin subset to omega 2, right? And S P omega 1 R is where C P plus what we want to do is basically argue like it's the same proof that we use to prove that anything else is well founded. Any other generic algebras will found it. That was the idea. Always was to show that the embedding agrees with the algebra by the club field, right? Okay, so what we do is we pick f from P omega 1 R into ord, and let S be S in VG. VG, it's enough to look VG, yeah, because of H. H is too closed. And in VG, V stationary subset of P omega 1 of R. So what we want to do, see, right, that there exists a function. We wanted to see that there is some other function. Want to see that there exists some f0 in B, such that no, I guess I want to prove yeah, I want to organize a bit differently, right? But I don't want to prove, well, I can state it that there is a function which agrees with f on a stationary set of points, right? But you probably want to, well, okay, let's do that. Such that for stationary many sigma in S, f of sigma is equal to f 0 sigma. So this would mean, so given this, we have that alt v, that then alt v u is well founded, or if u is generic for p omega 1 of r, well, let me just say ns p omega 1 of r. Because why? Because I can make right. I can find if you have descending sequence are functions like this, but that gives me descending sequence in the other ultra power, by the Club filter. So how are we gonna do it? Okay. So let okay, so let P force. So P force is that F is a function from P omega 1 of R into ord, and S dot is stationary, right? Okay, so forces that S is stationary. So this means not P forces S contains a club. Right? S complement contains a club. So if P forces S is stationary, then it's not the case that P forces S contains a club. So P does not force that S contains a club. Okay, so now if you go back to the definition of what that means, this is equivalent to saying, so by our lemma, this means that for omega many G, sorry, for club of sigma, for a club of, this is in V, yeah? For a club of sigma, for omega many G in P sigma. Okay, if G was forcing that sigma belongs to S, then we'll be in the other case where S dot complement. Then we will be in the case where that S dot complement contains a club. But we're not in that case. So what we have is that for omega many G, we have a condition extending it, which forces sigma belongs to S. So for a club of sigma for omega many G, there is a condition below G such that Q forces that this sigma belongs to S. Okay, so this is something you have to guys do in your head. First of all, why is it for club of sigma? Well, let's go back to the lemma. Right? The lemma is saying for a club of, if S contains a club, then you have for a club of sigma, for omega many generics G containing P, G forces sigma is in S. Now we have that P, this is false. So that means because club filter is an ultra filter, that means for club of sigma, the opposite has to happen, right? Okay, but that the opposite, if you just unravel it, is gonna be if you find that there will be comic of many G's where so we're talking about S dot complement, that you'll be able to find. So we're applying this lemma to S dot complement, not to S, right? So that means you will find any generic for comic of many generics, you'll find an extension which puts sigma into S rather than into S complement. So that's the equivalent thinking in this case. This is what we end up having. So there's always, for comic and many generics, I'll be able to extend it so that it puts sigma into S.
Can you say again why do you get omega many G? Why is this the complement? Because I see that the club filter is an ultra filter.
Right. And
why is it is that obvious?
Well, imagine so I think you probably wanna assume, okay, if there was an extension of S that P was forcing that S contains a complement, then you probably, I think you're right. I think I should probably take P such that no extension, an S. Let's see. So you want to say for Komigami, I think you probably want an S such that no P forces it is contains a club, right? Let's see. So what do we have? Of the above. Yeah, this is tricky. So we have P does not force S dot contains a club. So this means S dot complement. I think you want to look at P which forces it does not contain. Yes,
yeah, we can take a stronger P, right?
Right. I think this is what we want to do. Yeah. P forces. Yeah, we want to extend it. P forces S dot complement does not contain a cup, and then it's clear, right?
I think you want to have S complement or you want to have does not, because S should be, or is S stationary or not stationary?
S is stationary.
I see. Sorry.
But that's the thing, yeah. You want to take a stationary set. If it was already containing a club, then you can find the V club, so it will be easier. Now we can, if there is a condition that forces it contains a club, then okay, we can try to do that the other case too. Let's try to finish this one, right? So suppose, I guess I have to extend it. So suppose there is, let's call this one P0, right? Here I should say P0 is in G. Okay, suppose there is a, for all P less than P0, well, but then P0 forces S does not contain a cup.
Sorry, how is P0 different? What's wrong with P0 different than Q? Is P0 just Q or?
P0 is, let's see, no, P0 is something that forces, it's a function and S is a stationary set.
Okay.
And then we want to find an extension, right? I want to find a V function which matches this particular function. Okay, so it's just some condition. We want to work below it, but what if I can extend it that already contains forces that S complement contains. So that should have been an easier case. So suppose there is P extending P0 such that P forces S complement contains a club. Well, but P0 was forcing S is stationary. Wait, so wait a minute. P0 forces S complement does not contain a club. Yeah, sorry, I'm funny. P0 forces that S complement does not contain a club. Does not contain a club. This is that's the confusion, right? So there is no P0. Okay. And now we just let's see. So now we have omega many G, right? So if so now I'm gonna extend P to what I want. So now I have we have P extension of P0 such that means that there exists P extending P0 such that this happens, and this should be P. This is probably the correct state.
No, but now what's P is doing?
P is going to do the other, because you know it says comega, right? So it's not going to be that I pick a sigma, right?
Mm-hmm.
I know that P0 forces, if P0 was forcing S complement does not, let's see, S complement contains a club, then for omega many G would force. Is there a need for P?
Yeah, I just like to see syntactically even what.
Let's see. Suppose I pick P0, and now what is the negation of this statement? Let's go back to that statement. So the negation is saying for a club of the set of sigma for which there is a omega many G containing P such that G forces sigma is in S is not. So let's just write down that and then logically go see what happens, right? So we have that the set of sigma such that there is a omega set of G in G forces sigma check is in S dot is not a club. So what is a club? So what set is a club? So the set of sigma such that the set of G outside in P sigma, P is in G, and G forces sigma check is not in S, is in S, is omega. This is not in mu, so is not omega, right? So the set of sigma for which the set of this type of G is not omega is a club. Okay, so that set is not omega, which means what? Either it's meager or or it contains, or I can extend it to something that's Omega, right? So what is the G? So let's see, so the set of sigma such that the set of P is in G and G, and there exists Q extending G. Oh, I should have said as complement. Sorry, guys. This should have been as complement. Right? It should have been as complement. And there exists Q below G such that Q forces sigma check is in S. Is so this is not comega, that means its complement is not mega, yeah? Is a club. Because that was there I had is not comega, that means the complement, which is this set, right? Should be is not mega. And then that means, but not mega means I can extend it to comega set, right? So the set of sigma such that there exists P extending P0, P in sigma, and oh, this should have been P0. And P0, P is in G, and oh, Rahman came. And so P is in G, and there exists Q below G, such that Q forces that sigma hat is in S dot is omega below P is a club, right? So it's not meager. That means I can find P below which it is commeager. But now we do the for fineness, I mean normality, and we fix the P, right? So there is a P such that for a club of sigma, for commeager many G, containing P, there exists G subset of P sigma, right? There exists Q below G such that Q forces sigma belongs to S. Okay, that's how we get it. So what we get is this, that V thinks for a club of sigma for commeager many G with this property Q force, there is a Q which forces sigma is in S, right? Okay, and now what do we do? Well, now we use additivity of the meager ideal, right? So we look at the value of the function on these sigmas. And we know, because there are commeager many generics for which sigma is in S, right? We look at different Qs that I mean, look at there can each such Q below G is going to force a value for sigma, f of sigma, right? But there is one for which there are commeager many. So that's what we're going to do. I don't know if you, right? So now we look at, so now we said, we now said for sigma in the set above, and P is above, right? what do? We say F 0 sigma is equal to alpha, if and only if alpha is the least, such that for omega many G subset P sigma, which contains P, there exists Q less than G, such that Q forces that our sigma gets into S, and it also forces a value, and also it forces that the value of F at sigma is equal to alpha. Right? There has to be omega many G's with this. Oh, I see. This might involve, sorry, with this might involve another shrinking of P. Because it's we want omega many G, so there is P prime which is below P such that let's see, alpha is the least such that for omega many G with P and G, there exists Q there exists P prime less than or equal to P. No. Such that for non-mega, I should have said. Yeah. This is not right. So this is how we should be. Alpha is the least such that for non-mega many, for non, why would it be? I mean, we know that for omega many G, there is no P prime here. This should be P. Right? We know that for omega many G, I know I have something which forces sigma to be in S. But that means if I can find an extension also of that same thing, which forces F dot sigma is some ordinal alpha. Now, for each such alpha, which is a possible value, look at all these generics, right? For which there is a Q that forces this particular value. That's a well-ordered sequence of subsets of a omega set. We know that one of them is going to be non-mega because union of mega sets is mega. So one of them has to be non-mega. We cannot conclude that it is omega, but it's going to be non-mega. Okay. So alpha is the least such that for non-mega many G, with this property, I can, I have this. Okay, but then I can fix it on a omega set now, right? So we have by normality again. So we have P prime less than or equal to P, such that for club of sigma, F0 sigma is equal to alpha if and only if alpha is the least, such that for a omega now, omega many G, P prime and G, there exists Q below G, such that the Q forces sigma in S dot and F dot sigma equals alpha. Okay, so now we have, so now E prime forces what? That the set of sigma such that F0 sigma equals F sigma F check, sigma check, F dot check, and S dot is stationary. Right? Because I mean, club of such sigma force did I make a mistake somewhere? Because I ended up, it seems like I ended up that the set of such sigma is a club. I have to go. Thanks and see you next week. Let's see, I don't know. Let's see, what did we have? We had the P0 forces, Z and S is stationary. So S complement does not contain a club, right? So we have now for a club of sigma for common many G, P is in G. Oh, we want to find such a P. So why is that true? Oh no, there is a
Well,
Q. I think I wrote this is not true, right? P prime forces. This is stationary because there is a Q below P prime, not that P prime itself does not force that sigma is in S. Some other Q forces. So this is stationary, this set. Right? Why is this set stationary? Imagine you have a club. Imagine you have a club. Why is it intersecting it? Well, if I have a club, then what makes it stationary is the fact that there is a Q which forces sigma in S, not that G forces sigma in S. Right? So if you have a club, I can only prove that there is some sigma which belongs. I mean, you can prove that pick a sigma which comes from the above club and then find the generic, right? In other words, I cannot prove that any generic that contains P would evaluate this set as. Did I think something wrong? Yeah, I should have had stationary many. But stationary many means club many. I think I did something wrong somewhere. We have. So we know that P0 thinks S complement does not contain a club, right? So that means the set of sigma such that common many G's will put sigma in it as it's not a club, which means the complement is a club. So there's a club of sigma such that if I pick a generic containing P, G is not forcing that sigma is in S complement. So that means there is a continuation which forces sigma is in the complement, right? but there is also continuation which does not. So okay, so this P does not force. So all I can prove is that this P prime, if you give me a club, I can prove.
You can strengthen it so that you intersect.
Yes. Right. So it means it's a stationary set, not a. So if you take a club to let P prime prove something is a club, you can find
So
the
the last statement is not true, right? The
no, this
last
is
line.
true, I think. P prime forces that this is stationary. Why? Take a club. Then take a sigma which with the above property, with this property, with the property here, right? And suppose some extension of P prime forces that. Okay, let's just prove it. Yeah, why are we doing it? I need one extra page. Sorry, guys, that I'm going a bit over, but just for completeness. So why? Okay, so suppose there is some R which extends P prime such that R forces the set of sigma in S not such that F0 sigma equals F sigma is intersection, this club C is empty, where C is, right? And C is a club. Okay, so now we have sigma such that R is in sigma and omega many G, many G have an extension Q such that Q forces sigma is in S dot and Q forces also because of our construction, right? F, right? This Q is also going to force that it is F dot sigma equals this particular alpha. And that's what F0 sigma is also alpha, right? And V thinks F and what? And Q forces that F dot sigma equals F0 sigma. So there should be checks here. Okay, but Q is extending G and R is in sigma, so I can pick omega many G with R in sigma, with R and G. Why can I do R and G? Well, because I have omega many generics and R is an extension of P, so pick one generic which contains R, right? Omega many below R, RG, that's a better way of saying it. Because I have omega many generics below P, but R is below P, so you have omega many generics below P, below R. But now Q, but now Q is below R, so R forces R. So contradiction, right? So contradiction. All right.